Okay, so good evening everyone. I am Shivani Dhok and I welcome you all to the week 10 tutorial of the course of Digital Signal Processing and its applications. So like every week, this week's tutorial will also be divided into two parts. The first part will be recap of week 10 content, followed by the questions that are related to week 10 content. At any point of time, if you have any question, then you can just stop me and ask. Please unmute yourself and ask your questions, as I may miss your questions that you have posted in the chat box. If you have any question in the middle of any part that I'm solving, just stop me then and there. Don't carry forward that question till the end and then ask. It will be better for your understanding and understanding that particular thing in a better way. Yeah. Okay, so let's start with the recap of week 10 content. So this week 10 content carry forwards the concept of FIR filter that we started from the previous week, that is from week 9. And in this week, first we introduced various kinds of filter windows. So how do we construct FIR filter? We know the filter impulse response for the ideal filter, and what we know that the ideal filter impulse response is a sinc function which is of length which is infinite length, that is an infinite impulse response. But what we want is not infinite but finite. So what we do, we truncate that response symmetrically, and that truncation is made with the help of windows. The first window that we looked at in the last class was rectangular window. So this rectangular window is the very basic kind of window, and this window is basically, let's say I'll write it like this: WR of n is 1 for n belonging to minus n minus 1 by 2, or rather let me take minus n to n and 0 otherwise. Let it be of 2n length. Yeah. So now this particular window uh, has discontinuity here, or rather it is like a sudden truncation at both the ends, like at n equal to capital N and little n equal to n. So this kind of issues lead to what we call as ripples in the transition band, or rather ripples after the main lobe, and that is given by your Gibbs phenomenon. So in order to avoid those kind of things, and in order to have the side lobes with very less amplitude and a smooth transition, what we do, we introduced other kind of windows. One is rectangular window, another one is Hanning window. So I'll just write down the expressions for Hanning, Hamming, Blackman and Kaiser window. Rectangular window is simple, it has some slope, so that is okay. So this Hanning window is given by W of k is equal to half of 1 plus cos of 2 pi k by 2n. Then we have Hamming window. This Hamming window, this W of k is equal to 0.54 plus 0.46 into cos of 2 pi k by 2n. Then we have this Blackman window. This is W of k. This has two cosine terms. This is 0.42 plus 0.5 cos of 2 pi k by 2n plus 0.08 cos of 4 pi k by 2n. And the last one that we saw was this Kaiser window, and this is given by W of k equal to I naught beta n under root of 1 minus k by n whole square divided by I naught of tan. Okay, and this I naught here is basically the Bessel function, the zeroth order Bessel function of first kind. Okay, after that we looked at the windows and Gibbs phenomena. We said that we have some this Gibbs phenomena kind of things happening due to sudden truncation, and in order to smooth these things and in order to subside the side lobe amplitude, we go for these other things, other kind of windows. Then we compared the FIR and IIR filter. We figured out how much order both of them require, what are the complexities that are involved in that, and so on. And after that, we went on to another important concept, and that is realization of causal rational systems. And for that, we looked at two approaches. One was signal flow graphs, and another was pseudo assembly code. So in this lecture, we will look at few questions which are related to signal flow graphs, and some questions which are related to FIR filter design. So that's all from my side related to the recap of week 10 content. If you have any questions till this point, then please ask. Otherwise, I'll move on to the questions that I have planned to cover today. Okay, before moving ahead, I'll just write what this I naught here is. So this I naught here is zeroth order Bessel function of first kind. Okay, if there are no questions, then let me move on to the sample questions or solving questions that I have planned to cover today. Okay, let's start with the first question. So the first question here says that a rectangular window sequence takes value 1 between little n between 0 and 5, and it is 0 otherwise. What is the Fourier transform of this signal? So what is given to us? So given to us is a rectangular window sequence. Let's say it is given by W of n, and this sequence takes the value 1 between 0 and 5. So this is 1 when I have this n between 0 and 5, and this is equal to 0 otherwise. Okay, so this is given to us. So how does the sequence look? So this looks something like this. This is n. Here we have W of n. Let me extend it a little bit on this side as well. Then we have 1 here at 0. 1, 2, 3, 4, 5, 6, 7, and so on. And then we have minus 1 here and so on. So this is 1 for n equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. And it is 0 otherwise. Okay. So this is how this signal look like. And what we need to find? We need to find its Fourier transform. So this W of n, let's say it has a Fourier transform of capital W of omega. So this is the DTFT of W of n. Okay, so let's now find out the DTFT of this signal W of n. So this DTFT of W of n, which is capital W of omega, this is given by definition as summation n running from minus infinity to infinity W of n e power minus j omega n. Okay, now this thing here, this W of n is non-zero only for the values of little n of 0 to capital 0 to 5. So this summation here will survive only for values of n equal to 0 to 5. So this is equal to summation n equal to 0 to 5, and in this range my W of n is equal to 1 into e power minus j omega n. Okay, so this is basically summation n equal to 0 to 5 e power minus j omega n. Now if you observe carefully, what is this? This is basically a geometric progression, a finite geometric progression. So this is a finite geometric progression with first term as, if you put n equal to 0 here, you get 1. With first term as 1, common ratio as e power minus j omega, and number of terms is, it starts from 0 and ends to 5. So there are total 6 terms. Okay. So therefore this summation here is equal to first term into 1 minus common ratio to the power number of terms, that is 6, divided by 1 minus the common ratio. Okay, so now we can write this as 1 minus e power minus j 6 omega divided by 1 minus e power minus j omega. Now we'll do little bit manipulations here. In general, when we get such kind of expression, you need to simplify it further. Even in your exams, when you will get options, you will get a simplified option and not in this form. Okay, so you can now write this as, or rather from the numerator, you can take out e power minus j 3 omega common. So you can write this as e power minus j 3 omega. So inside the bracket, it will be e power j 3 omega minus e power minus j 3 omega. And from the denominator, you can take out e power minus j omega by 2 common. So e power minus j omega by 2. Inside the bracket, you will have e power j omega by 2 minus e power minus j omega by 2. Now what do we get? Now we can divide the numerator and denominator by 2j. So this part here can be simplified as e power minus j omega 3 minus half, and the numerator, if you look at this part, this is nothing but sine of 3 omega. So the numerator is sine of 3 omega, and similarly the denominator is sine of omega by 2. And how am I writing this? This comes from the simple thing, that is sine of theta. We can write as e power j theta minus e power minus j theta by 2. So for the numerator, this theta here is equal to your 3 omega, and for the denominator, this theta is simply omega by 2. 2j. Yeah. Okay, and this thing here is basically 2.5. So what we get now as the final answer is W of omega is equal to e power j 2.5 omega into sine of 3 omega divided by sine of omega by 2. And this is the final answer. This is basically your DTFT of given W of n. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Yeah. Okay, so this question looks a little bit long one. So we'll read it step by step and try to simplify and try to understand what is being asked to us. Okay, so let's start. So what is given to us is we have to design a high pass filter with FP as 300 Hz and Fs as 200 Hz, which exhibits attenuation greater than 40 dB in the stop band. So this 40 dB is basically your stop band attenuation. Okay. Then it is said that we need the pass band ripple to be less than 0.2 dB. So the pass band ripple is less than 0.2 dB. Now it is said that assume that the sampling frequency to be 1200 Hz. So your sampling frequency is given to us as 1200 Hz. And the limits in the pass band and stop band attenuation correspond to the magnitude response and not the magnitude squared response. Okay. Now what we need to do is we need to find the approximate window length if a Hanning window is used to design this filter. Okay. So what all things are given to us? First thing that is given to us is it is a high pass filter. So the pass band edge in analog domain is FP, which is 300 Hz. And before that, I'll just write down the sampling frequency. Okay, let it be. We'll do it afterwards. Yeah, then we have the stop band edge, which is Fs equal to 200 Hz. Then we are given sampling frequency, and the sampling frequency, let's say F sam, this is equal to 1200 Hz. And there are some pass band and stop band attenuations also given to us. We'll see what do we need them or not. Now what is asked to us is we need to find the approximate window length if a Hanning window is used to design this filter. Okay, so what we will say is the aim is what is the window length if we want to design high pass filter using a Hanning window. Okay, and what things do we know about this Hanning window? This Hanning window of length to n plus 1 has a main lobe width as 4 pi by n. Okay, so this is what we know about this Hanning window. And another important thing that we need to know is this main lobe width is responsible for the transition width or the transition band length or size of the filter. So this main lobe width of Hanning window, or for that matter any window, is equal to transition width of the filter. Okay, so what do we know? We know this. Okay, so let me just write this as WT. And this transition width in angular domain of the digital filter. Okay, not the one given in your Hertz frequency. So this is angular domain for digital filter. Okay, we need to be careful in this. So what relation do we have now? So therefore, we have 4 pi by n to be equal to the transition width, that is, let's say, omega t. Okay. Okay, so therefore, this n is equal to 4 pi by omega t, which means that this window length is basically 2n plus 1, which is equal to 8 pi by omega t plus 1. So in this equation, what we don't know? We don't know what is the value of this omega t. This is the thing that we don't know. But what is given to us? We are given the passband and stopband edges. And using these passband and stopband edges, we can figure out this transition width. So the transition width omega t is given by, this is a high pass filter. So this will be given by omega p minus omega s. Okay. So now let us first figure out what is the value of omega p. So therefore this omega p is equal to 2 pi, we need to normalize them. So 2 pi fp by f sampling, which is equal to 2 pi fp here is given to us as 300 hertz. And we are given the sampling frequency as 1200 hertz. So what is left with us is pi by 2. And similarly, omega s is given to us as 200 hertz. Sorry, omega s is equal to 2 pi fs by fsam, which is equal to 2 pi fs is basically 200 hertz, that is given to us, divided by 1200, and this comes out to be equal to pi by 3. So therefore, omega t is equal to omega p minus omega s, which is equal to pi by 2 minus pi by 3, which is equal to pi by 6. Okay. Now let us take this and substitute it in our window length. So therefore, window length is equal to 8 pi by omega t plus 1, which is equal to 8 pi upon pi by 6 plus 1. which is equal to 48 plus 1, which comes out to be equal to 49. Okay. So therefore, the length of the filter, sorry, yeah, the length of the filter or window is equal to 49. Is it clear? Any questions till this point? Any questions? Is it clear? Okay, I assume it is clear. Then we can move on to the next question then. So this is also a filter design question, and this is very similar to a question which we had covered, I think 1 or 2 weeks back. I think 2 weeks back. So what is given to us is, this is the common data for question 3 to 5, and what is given, or what are the aim of this question is to design an FIR filter with Kaiser window. And here are the specifications that are given to us. So this first specification is, we want to design a filter for a band limited signal, and that signal is limited to 160 kilohertz. Okay. Now the tolerance of this filter in pass band and stop band is 0.15. Okay, so this is the pass band and stop band tolerances. So this is equal to your delta, which is equal to 0.15. And then we are given the sampling frequency, that is fSam, which is equal to 330 kilohertz. And then we are given the pass band edges, that is 85.7 kilohertz and 105.7 kilohertz. And then we are told that the transition width is of 4 kilohertz on either side of the pass band. So here we have FP1, which is 85.7 kilohertz, and then we have FP2, which is 105.7 kilohertz, and then we are given the stop bands. This is FS1, which is 85, rather FP1 minus 4, that is 81.7 kilohertz, and then we have the FS2, which is 105.7 plus 4, so that is basically 109.7 kilohertz. So these are the specifications that are given to us. Now let us walk through. Let us walk through to get whatever things we need for getting this filter and the Kaiser window. Okay. So what is given to us is, find the what is asked in this question 3 is the value of minimum stop band attenuation parameter A in Kaiser window. First we need to find that. So what is it? So for Kaiser window, just a moment. Yeah, for Kaiser window, the minimum stop band attenuation parameter the minimum stop band attenuation parameter A is given by A is equal to minus 20 log delta to the base 10, and this is equal to minus 20 log. What is the value of delta given to us? Let's go back to our specification. So it is given to us that the tolerance in the passband and stop band is 0.15. So this is the value of delta that is given to us. So let us substitute it here. So 0.15 to the base 10. And of course, you can't find it manually. You will have to use your calculators. And this value, when after using calculators, comes out to be equal to 16.478 dB. Is it clear? Any questions? So this is the first parameter that we need to figure out in order to design our Kaiser window. But if you observe carefully, the Kaiser window equation that is in the form of your Bessel function, that depends on two factors. One is your beta, another is n. These are the two parameters on which it depends. However, these two parameters can be obtained with the help of the A, that is the stop band attenuation factor that we have used. Now using this, now we will find out the beta and the n. Okay, so now we need to find out the shape parameter beta. Now, in order to find this shape parameter, there is another parameter that is known as alpha, which is basically n times beta. So this alpha is n times beta, which means that this beta comes out to be alpha by n. Now, what is this alpha? This alpha is given by, or this alpha is basically a function, or alpha is basically a function of A, and rather it depends on what value A takes. So for that it has three cases. So the first one is this alpha is equal to 0 when my A is less than 21, and this is in dB. A is less than 21. Then we have alpha to be equal to 0.5842 into A minus 21 to the power 0.4 plus 0.07886 into A minus 21, and this is for A in the range of 21 to 50, and this is equal to 0.1102 into A minus 8.7 for the values of A that are greater than 50. Okay. Now what value of A did we get? For our case, A is equal to 16.478 dB. So for our example, A is equal to 16.478 dB, and this basically lies in this range. That is, my A is less than 21, and therefore alpha is equal to 0, which also implies that my beta, which is equal to alpha by n, this also comes out to be equal to 0. Is it clear? Any questions? So this is one of the parameter that we need to figure out with the help of our given specifications. Okay, if there are no other questions, then let me move on to the next question then. It says that now we need to find the minimum value of n. So since I had copy pasted this question from last year's assignment, I have just added the way it was given in the on the website. Okay. Okay, so this is the question. Now we need to find the minimum value of n. So n, or rather for a Kaiser window, this length of the filter, that is 2n plus 1, is greater than or equal to 1 plus a minus 8 divided by 2.285 omega t, where again this omega t is transition width. Okay. In our specifications, we are given transition widths. So these are basically my FTs. We have these transition widths. These are our transition widths. And we will be using this. So these are basically in analog domain. However, this omega t here is basically the digital angular frequency or normalized frequency. So this is basically equal to 2 pi ft by fsan. Okay. So this comes out to be equal to 2 pi ft is given to us as 4 kilohertz divided by sampling frequency, which is given to us as 330 kilohertz. So if we simplify this, this comes approximately equal to 0.024 pi. Okay, so now we know A, we know the value of omega t. Now let us figure out what is the minimum value of n. Okay, so let us substitute these values, omega t equal to this and a equal to 16.478 in this equation to get the minimum value of n. So what we have, let me just rewrite the formula here. We have 2n plus 1 to be greater than or equal to 1 plus a minus 8 divided by 2.285 omega t, which is equal to 1 plus a is equal to 16.478 minus 8 divided by 2.285 multiplied by 0.024 pi. So this 0.024 pi is basically the transition width, and if we simplify this, this comes out to be equal to 50.209. So now what we have, therefore 2n plus 1 is greater than or equal to 50.209, which means that n is greater than or equal to 50.209 minus 1 divided by 2, and when we simplify this, this comes out to be equal to, or rather since we want a minimum value, we'll take a seal here. So this comes out to be equal to 25. Okay. So n is the value of n equal to 25. So for minimum, n rather minimum value of n is 25, and if we want to be precise, if the length of the filter is 2n plus 1, then the order of the filter is 2n. So So therefore order of this filter is 2n, which is equal to 50. Now I would like you to recall something, maybe last week. So recall. So let me just quickly go to that. Just see if it is this question or what. Yeah. So this is basically exactly the same question which we had solved in the week 8 tutorial of this course. Exact same specifications, but for this we had used a Butterworth filter. Okay, and we had found out the order of the equivalent low pass filter. So the order of the equivalent low pass filter we had found out as n equal to 8. Okay, and using this we had to find out the band pass filter. So when we simplify it and we substitute and we do everything, what we observe is we have this s square terms appearing n times. So the order of the band pass filter is twice the order of your equivalent low pass filter. So when we did Butterworth filter or an IIR filter for the same given specifications, the order that we got was this 2 into 8, that is 16. So recall, in week 8, tutorial, we designed this band pass filter with exact same specifications using Butterworth IIR filter design approach. Okay, for this filter, we had got the order of band pass filter as 16, and for this filter, for FIR filter with Kaiser window, order is 50. So if you observe carefully, this is almost 3 times the order of our IIR filter. So to get the same kind of specifications, we need much more resources in FIR filter compared to an IIR filter. So this is what I wanted to show with this particular example, because we had designed this filter using IIR approach in previous weeks. So this is basically the difference that you will have or that you get. Now since I have time, what I'll do is I'll also construct the window now. So what was the formula for our window? So the window formula is given by this here. So this beta into n, beta had come out as 0. So now what we get I naught of 0 upon I naught of 0, which is equal to 1, which means that this is now reducing to our simple rectangular window. Is it clear? Any questions till this point? If you have any questions till this point, please feel free to ask. This was the last question that I wanted to cover related to filter design. After that, I'll move on to uh, system realizations. Okay. Another suggestion is you please go at your home and try to solve all of these filter design questions, especially IIR filter designing questions on your own. If you have any queries, just put it in the question and answer portal on the NPTEL website. And if it is urgent, I'll answer it at the same time. Otherwise, I'll carry forward those questions till the summary session just before your exam, final exam. Okay, if there are no further questions, let me quickly move on to the next question that I have planned to cover today. From now, the questions will be simpler because these are realization based questions. So hopefully these will be simple to understand compared to the filter design part. So the hard part is done now. We'll just look at the simpler questions. Sorry. Yeah. Okay. So the first question here says that find the number of adders, constant multipliers with gains not equal to 0 and 1 and a unit delay buffer used to realize h of z using the signal flow graph of direct form 2. Okay, so this is the system function that is given to us. This is basically equal to y of z upon x of z. Now this y of z I can write as, or rather I can simplify this as y of z into 1 plus 2z inverse minus z to the power minus 3, which is equal to x of z into 3 minus z inverse. Okay. Now what I can do, I can write this as y of z plus 2z inverse y of z minus z to the power minus 3 y of z, which is equal to 3x of z minus z inverse x of z. Now I can take inverse z transform. Inverse z transform of y of z is y of n plus 2 times z inverse y of z has inverse transform as y of 2 times y of n minus 1 minus y of n minus 3, which is equal to 3 times x of n minus x of n minus 1. So now what I can do, I can shift all the terms other than y of n to the right hand side. So therefore y of n is equal to 3 times x of n minus x of n minus 1 minus y of n plus 2 times y of n minus 1. Did I write? Sorry. Minus 2 times y of n minus 1 plus y of n minus 3. Okay. So let me add a page. Now what we will do, we'll first construct direct form 1 and then construct direct form 2. I'm doing it on purpose just to compare the number of adders and subtractors that, adders and gain multipliers and all those things that are required to us. So this is not needed, but let me do it since we have some time. So first thing we'll do is for direct form 1, or let me modify the questions for direct form 1 and direct form 2. So let me do it first for direct form 1. And how to construct direct form 1? What we will do, we have x of n here. Then this x of n gets multiplied by 3. So here what do we get? Here we get 3 times x of n. Now this x of n is also having a delayed version and scaled by -1. So this x of n, we can delay it by minus z inverse. Let me take the same notation as the class. So we have z inverse, and the z inverse gets scaled by -1. -1, and this gets then added like this. Okay, so what do we have here? What are we getting here? At this point we are getting 3 times x of n minus x of n minus 1. So this is this part. Sorry. Now after this part we need to construct the remaining part, that is this one. This gets added. So what we do is, we know that the output here is y of n. This is y of n. Here, and we know that this gets added here like this. Like this here, let's say. And at this point we have this term coming, and these terms need to get added at this point. So what happens here? We have this y of n, and this y of n first gets delayed by 1 unit, that is z inverse. So here we'll get y of n minus 1, and that gets scaled by -2. -2, and this will get added to this one. Now still we need few things. We need this y of n minus 3. So again we'll delay this y of n by 1 unit. Yeah, z inverse. So now what we will get? We'll get y of n minus 2, but we want y of n minus 3. So again we'll delay it by 1 unit, z inverse. And this gets added here. Okay, so what we have here now at this point, at this point we have, after merging of both of these, we have y of n minus 3 minus 2 times y of n minus 1. So this thing now gets added to this particular thing here, and that gives us our final y of n. So this is the direct form 1 representations. And now what we need to find? We need to find the number of constant multipliers, adders, and unit delay buffers. So let us first go step by step. Let's do adders first. So first we will do adders. How many adders do we have? How to identify adders? It should have 2 incoming arrows and 1 outgoing arrow. Okay, so in that fashion, how many do we have? One is here, here, then another one is here, then we have an adder here also. So here one is here, then we have here, and then we have here. So number of adders is equal to 3. Then we will have number of constant multipliers other than 1 and 0. How many are these? Let us calculate. So one is here, then one is here, then here it is 1, here also nothing, here also nothing, here also nothing, here also nothing, here. Okay, so we have a -2 here. So number of constant multipliers is equal to -2. Sorry, 3. Yeah. And the last thing that we need to calculate is the number of delay buffers. So we'll calculate delay buffers. How many do we have? One we have here, then one we have here, one here, and one here. So total we have 4 delay buffers. Is it clear? Any questions till this point? Okay, if there are no questions, then let me go on and do the same thing for direct form 2. And how do you get direct form 2? It's simply a changed version of this direct form 1. So what we'll do, we'll interchange the locations of these two and share the buffers. So how does it look? I'll just copy paste it. Copy paste this thing first. So here what we do, here first we construct this part. Okay, but x and y both locations are same. So here we have x of n. X of n is here. Then bring it to this point. Then we have z inverse. Then this gets scaled by -2, and this then gets added here. Then again we want this y of -3, so z inverse one time, and then one more time we have z inverse, and now this gets added like this. Okay, now this part is done. Next thing that we need to do is we need to construct these things. So this we have a scaling by 3, that will give me x of n here, 3 times x of n, and then we have a delay here of 1 unit, and then we get it scaled by -1, and this gets added like this, and this is the y of n that we get. So this is exactly the shifted or rather interchange version of the direct form 2. Okay. Yeah. So now now again we'll find these 3 things, that is adders, constant multipliers, and delay buffers. So let us first start with adders. Let me use black color here. How many adders do we have? Let's calculate. So we have one adder here, another adder here, then we have one adder here. This is simply branching out There is no adding operation happening here. Here also, this is simply branching out. This one thing is coming inside and that gets branched out like this. So there is no other adders. So we have 3 adders. Next thing is constant multipliers. How many constant multipliers do we have? One is located here, another one is here, and another one is here. Rest all are 1. Okay, so let me mark them properly. One is located here, another is located here, and another is located here. So the number of constant multipliers are again 3. And the last one is the number of delay buffers. How many delay buffers do we have? One is here, another is here, and another is here. So we have total 3 delay buffers. So if you observe carefully, for direct form 1, the number of, for direct form 1 and direct form 2 both, the number of adders were 3, the number of constant multipliers were also 3. But the only difference that we are getting is in the number of delay buffers. For direct form 1, the number of delay buffers were 4, and for direct form 2, the number of delay buffers is 3. So in terms of the resources, direct form 1 is using less resources compared to the direct form 1. Is it clear? Any questions? Okay, if there are no questions, then before moving ahead, I will just give you a few tricks on how to get your direct form 1 and direct form 2. So for that, you don't have to do all of this business. You can simply observe the given system function and use it. Just a minute, I'll take a screenshot of this. Sorry. Yeah, so let me paste it here. So this is a transfer function that is given to us, and if you want to construct a direct form 1, what you can do is you can start with the numerator. So your x of n comes, then first thing, if you have a constant or a constant here, a constant that is not equal to 1, then 3. So first you add a constant multiplier block of 3, then you have minus z inverse. So now you bring a z inverse here and get it multiplied by whatever coefficient it has here. So therefore you have minus 1 here. Now if you have, now this numerator part is done. Next thing that you need to focus is on the denominator part, and the denominator part will contribute in this side. Now for this, if you have a a non-1 constant here, so here you will multiply it by that constant. Let's say you have a c here, so then you will multiply this part by c. Okay, then you have a 2z inverse. So you have a z inverse, but now instead of 2 you will put minus of that whatever coefficient you have. So minus 2, and that you add with this. Similarly, whatever delay blocks you have, you create those, get them multiplied by the negative of their coefficients. So you have a 1 here, not minus 1. Negative of the coefficients, and then add it. So this is how you will do for direct form 1. It is very simple. By just observation, you can construct it. Now for direct form 2, you start in the opposite fashion. Okay. You start with the denominator. You start with the denominator, that is, just a minute. Yeah, here. Okay. You start with the denominator. You have a 1 here, that 1 will remain as it is. Then you have a z inverse. And that z inverse will get multiplied by negative of the coefficient, that is minus 2. Then you have minus z to the power minus 3. So 1 delay, another delay, and then again multiply it by minus of the coefficient of z to the power minus 3 and add it. Now this part corresponds to your denominator. Now you go to the numerator. Now this is where you can start. First multiply it by the constant whatever you are having here. And after that, you focus on the delays. So this delay z inverse we have, and that gets multiplied by a minus 1 here. And then you add it. So just by the observation, you can figure out how to do or how to construct it. You will get it by practice. You need to practice more examples for this. Is it clear? Any questions? Okay. If there are no questions, let me move on to the next question. So this question says that for a signal flow graph, give the system function. So this is the signal flow graph that is given to you. And now we need to use this to get the system function. So let us do it one by one. Let me zoom it. It's a little bit blurry image, but okay. Okay. So this is the x of n that we are having here. So at this point, we have x of n. Use the thinner version of pen. We have x of n. Now this x of n is moving here and also here. You just look at the arrows. Okay. So this gets distributed along this direction as well as along this direction. So basically here we have x of n, and that x of n gets multiplied by 8. So at this point here we are having 8 times x of n. Okay. Now this x of n was also, this x of n was also carried forward here. So here also we have an x of n, but now that x of n is getting multiplied by z inverse. So here you will get, at this particular junction, you will get x of minus n. X of n minus 1. Okay. And similarly, this x of n minus 1 is going here also, and it's going here also, on both the directions. So here you have x of n minus 1, and when you come to this point, you will get 10 times x of n minus 1. So at this point, you have 10 times x of n minus 1. Till this part, is it clear? Okay. Now along with that, this x of n minus 1 is going along this direction also. But now you have a delay block here. So now this will shift this x of n minus 1 by 1 unit. So now you'll have x of n minus 1 minus 1. So that will give me at this particular point x of n minus 2. Now this x of n minus 2 goes along this direction, but it gets scaled by 15. So here at this part or at this point, you will have 15 times x of n minus 2. Now this 15 times x of n minus 2 goes here and gets added with whatever was located or whatever we have obtained here. So therefore, at this point, we will have addition of whatever is available here and whatever is available here. So what do we get? We get 10 times x of n minus 1 plus 15 times x of n minus 2. Now in similar way, whatever is available here gets added with whatever was available along this line, and it gets added here to give 8x of n plus this quantity. So at this part, at this junction, we get 8x of n, which is coming from here, plus 10 times x of n minus 1 plus 15 times x of n minus 2. Okay. So for one part of this we have done. Okay. Okay. Yeah. This. Yeah. Now since it is very crowded, I'll just copy paste the same image here and use it. Yeah. Okay. We have it here like this, and what we have found out at this particular point. At this point, we have found out what we have got. So I'll just write it this point, exact this point. What we have got, I'll just write it down. I'll write it this side. Yeah. So we have 8 times x of n plus 10 times x of n minus 1 plus 15 times x of n minus 2. Okay. Now this thing gets added, this thing, whatever we just wrote or whatever is available here gets added to whatever is coming from this side. So now let us try to understand what exactly is the output at this point. Okay. So now here, since this part is y of n, this point is also having y of n. Okay, so now this y of n is going along this direction and it gets multiplied by z inverse, which means we get here we are having y of n minus 1, that is delayed version of y of n. Okay, now this y of n minus 1 goes along this direction and gets multiplied by 12. So here you have 12 times y of n minus 1. And now this 12 times y of n minus 1 goes here and gets added with this term here. Okay. So now after this addition, at this point, at this junction, what do we get? We get 8 times x of n plus 10 times x of n minus 1 plus 15 times x of n minus 2 plus this 12 times y of n minus 1. Okay, and this gets traveled to this point. So basically this point here and this point are exactly the same. So what we have got now, we have got this is equal to our y of n. So what do we have? So therefore, what did we get? Therefore we got y of n equal to 8 times x of n plus 10 times x of n minus 1 plus 15 times x of n minus 2 plus 12 times y of n minus 1. So this is the difference equation that we have got. But what is asked to us? We are asked to find the system function. So now we need to find out the z transform. So in order to do that, before finding z transform, let us collect the terms of y's on left hand side and all the terms corresponding to x of n's on the right hand side. So therefore what we get, y of n minus 12 times y of n minus 1, it is equal to 8 times x of n plus 10 times x of n minus 1 plus 15 times x of n minus 2. So now let us find the z transform. So what we get, therefore y of z minus 12 times z transform of y of n minus 1 is z inverse y of z, which is equal to 8 times x of z has a transform, x of n has a transform as x of z plus 10 times x of n minus 1 has a transform as z inverse x of z plus 15 times z to the power minus 2 x of z. So therefore y of z I can take out common, we get 1 minus 12 times z inverse, which is equal to, I can take out common x of z, which is equal, so x of z into we have 8 plus 10 z inverse plus 15 z to the power minus 2. So now what we get y of z upon x of z, which is basically our system function, which is h of z, that comes out to be equal to 8 plus 10 z inverse plus 15 z to the power minus 2 divided by 1 minus 12 z inverse. Is it clear? Any questions till this point? So this is the system function for our given signal flow graph. Any questions? Okay, if there are no questions, then before I go ahead, instead of going, I'll give you a small trick. Instead of going through this long process, you can again do it by observation. So let me just paste the same signal flow graph that is given to us. So this is the opposite thing of what we had done uh, in our previous things, or getting the signal flow graph from the transfer function. So we'll do the opposite thing now. We'll get the transfer function from the given system function, given signal flow graph. So what we wanted h of z. And to be precise, this particular representation is direct form 1. Okay, so now we had seen that when in the previous question we had seen that this part corresponds to the numerator and this part corresponds to the denominator, and we had seen that this is the constant that gets added, then this part is 10 times, or this part corresponds to the second term, that is 10 times z inverse, and this corresponds to the third term. So you can write this h of z as this constant 8, then this coefficient 10 is the coefficient of z inverse term, so plus 10 z inverse, and this coefficient is basically the coefficient of the z to the power whatever number of delays you have. So we have z inverse into z inverse here, so you need to multiply all the z inverse that are there before this particular thing. So this is basically plus 15 times, we have z inverse into z inverse, that is 15 times z to the power minus 2 divided by. Now here is the constant term that we have here, wherever you put, it's okay. So you have 1 plus minus times whatever is present here multiplied by z inverse. So minus times 12 z inverse. So if you compare this and this are exactly the same things. So what we did, this is what we get here, then this is what we get here, and this thing is what we get here. Okay, then what do we have? Next thing is this y of n, this term comes here, then we have 12 times z inverse, so that thing comes here. Is it clear? Any questions? This is a small trick that you can use. This is simply by observation, so you can get this h of z by simple observations. Any questions? Okay, if there are no questions, then let me move on to the next question. So this is the question number 8, and it says that how many delay unit delay elements would be needed to realize h of z in the direct form 1, given that nn and bm are not equal to 0. Okay, sorry. Yeah, okay, so let's do that. It is direct form 1 representation. So direct form 1 representation is simply like representing this equation step by step like this. Okay, so let us do that. So here we have y of z upon x of z. We'll repeat the same process. So when we cross multiply it, what do we get? We get y of z multiplied by 1 minus summation n equal to 1 to capital N n z to the power minus n which is equal to, or let me do this, I'll just use this k instead of n. K, 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 yeah, like this, which is equal to x of z multiplied by summation n running from 0 to m dm z to the power minus m. Okay, so y of z is equal to summation m running from 0 to m dm z to the power minus m x of z plus summation k running from 1 to n ak z to the power minus k y of z. Now if I take inverse z transform, what do I get? I get y of n equal to summation m equal to 0 to capital M b of m z to the power minus z to the power minus m x of z has z transform, inverse z transform as x of n minus m plus summation k equal to 1 to n a k's into y of n minus 1. Okay, so let me add a page. So now I can write this as y of n equal to summation, or rather I'll take out the b 0th term outside, b of 0 x of n plus summation m equal to 1 to m b1 or bm x of n minus m plus summation n equal to 1 to n a k's y of n minus k. Yeah, this is k here, not 1. Okay, so this is what we have. Now what all things do we need to figure out? We need to find the number of delay elements that are required to realize this system h of z. So okay, so now if you observe here, this part b0 into x of n, x of n is the current input, so for this you don't need any delay elements. So for this, no delay elements required. Okay, now just focus on this summation part here, first summation, this one. Okay, now you need to get, for getting these things, so this summation has total m terms, and in every term you are delaying this by 1 unit. Okay, so first one you will give you x of n minus 1, then you will have x of n minus 2, you will have x of n minus 3, and so on till x of n minus capital M. Okay, so therefore in order to get this particular thing, we will need total m number of delays. M delays needed. And similarly, exact same way, for this particular summation, we have this summation running from n equal to 1 to capital N, and this will give me basically y of n minus 1, y of n minus 2, and so on till y of n minus capital N. So like that, I will have total n number of delays. So n delays needed. So therefore, total number of delays are given by the number of delays required to realize this summation and the number of delays required to realize this summation, and that is given by m plus n. And this is for what? This is for direct form 1. Is it clear till this point? Any questions? Okay, if there are no questions, then let me pose a question then. These number of delays are for your direct form 1. What happens if you have to do it for direct form 2? What happens when we need to do the same thing for direct form 2? Okay. Now for direct form 2, what happens? We interchange the positions of two subsystems and we share the delays. So this summation and this summation, sorry, yeah, this summation and this summation, they share the delays, which simply means that the number of delays that are required to us will be maximum of these two values. So if this summation has more number of elements, more number of delay elements, and since we are sharing, we'll have to serve its demands of having more delays. So if m is greater than n, for example, if this m is 3 and n is 2, we'll need 3 delays. Similarly, if this m is 1 and n is 5, then we will need 5 delays. Okay, so now just to make a note of it, for direct form 2, since we share the delays, the number of delays required, or the number of unit delays required are max of m and n. Is it clear? Any questions till this point? This point is clear to you? This, the one for direct form 2. Okay. Okay, if this part is clear, then let me move on to the next question. Just a minute, let me drink water. Yeah, okay. So this is the 9th question that I have planned to cover today. So it says that if y1 of z divided by x1 of z is of the form of 1 minus az inverse into 1 plus az inverse, then if a and b are real numbers with magnitude less than 1, so this a and b that are given to us are having magnitude less than 1, then the values of k1 and k2 also have the values less than 1. And they are asking whether this statement is true or false. Okay, so this is what they are asking to us. So let us first simplify this thing a little bit. Let us first understand where this y1 of z is. So this diagram is really bad. This here we have this y1 of z, and here we have x of z, and we are given y1 of z and divided by x1 of z. So this is basically your output, this is input. So output divided by input is given to us as like this. And now we need to figure out what values or what ranges of this what ranges this k1 which are located here and this k2 can take. Okay, so let us first try to get y1 and y1 of z upon x1 of z in terms of k1 and k2. Okay, yeah. So first let us figure out what this y1 of z looks like. So this y1 of z is basic. Okay, no, let's not do that. Let us start from the input part only. Yeah, okay. So this is this is my, sorry, yeah, this is my x of z. This x of z goes here and here. So at this point we have x of z, and here also we have x of z. Then this x of z here gets multiplied by z inverse. So here at this point we have z inverse x of z. And then this z inverse x of z is carried forward in the same way at this location also. So here also we have z inverse into x of z. I'm sorry. Yeah, okay. So we have z inverse x of z here, and at this particular location, what do we get? We get the z inverse x of z as it is, and from here we get x of z that gets multiplied by k1. So here we get z inverse x of z plus k1 into z inverse. Sorry, k1 into x of z. Okay, now at this location, at this particular location here, we get this x of z as it is, and then the z inverse x of z gets multiplied by k1 and gets added here. So this y2 of z, whatever we have here, this y2 of z is equal to x of z plus k1 times z inverse into x of z. So this y2 of z is equal to x of z plus k1 times x1 of z inverse x of z. And now we have this y1 of z here. So to get this y1 of z, it is basically summation of y2 of z as it is plus whatever we are getting at this part. For that, at this location, we get z inverse multiplied by whatever we had here. Okay, so we get z inverse multiplied by these terms, that is z inverse x of z plus k1 into x of z. And let's say this is sum x2 of z. So here we get x1 of z as y2 of z plus x2 of z times k2. Okay, so therefore what do we have? Therefore y1 of z is equal to y2 of z plus k2 times x2 of z. So what do we get? This y2 of z we had obtained as x of z plus k1 z inverse x of z plus this x2 of z we have obtained as, so we have k2 times z to the power minus 2 x of z plus z inverse k1 x of z. So let me write it down properly now. So what do we have? We have therefore y1 of z is equal to x of z as it is, plus I'll club the terms that correspond to z inverse. So this term and this term I'll club. So plus z inverse x of z. Then I have, from this term I have k1, and from this term I have k1 multiplied by k2 plus k1 k2, plus we have z to the power minus 2 k2 into x of z. Now I can divide both sides by x of z. So what I get? y1 of z divided by x of z. This comes out to be equal to 1 plus k1 into 1 plus k2 z inverse plus k2 into z to the power minus 2. And this is given to us that this particular thing takes the form 1 plus az inverse plus 1 plus az inverse into 1 plus bz inverse. So let me write it down. Given is y1z upon xz is equal to 1 plus az inverse multiplied by 1 plus B Z inverse. If we simplify it, it comes out to be equal to 1 plus A plus B Z inverse plus AB Z to the power minus 2. Now if we do pattern matching of both the equations, that if we compare the coefficients of Z inverse to the power K in both of these equations, this one and this one, what do we get? We get the coefficient of this Z inverse is equal to A plus B, and similarly the coefficient of Z to the power minus 2 is equal to A minus B. So therefore, by comparing, we get K2 is equal to AB and K1 is equal to A plus, sorry, K1 into 1 plus K2 is equal to A plus B. Is it clear? Now what we need to find out? We need to figure out if A and B are having magnitudes less than 1, then can K1 and K2 also have magnitude less than 1? So let us try to do that. So let us first do for K2 for this equation. Since K2 is equal to AB, which means that magnitude of K2 is equal to AB, or magnitude of AB, which is less than or equal to magnitude of, which is rather equal to magnitude of A into magnitude of B, and magnitude of A is less than or equal to 1, and magnitude of B is also less than or equal to 1, so therefore this is also less than or equal to 1. So this is giving me that magnitude, or let me write it like this, K2 is less than or equal to 1. This is for sure. Now what we need to check is, we need to check for K1. Okay. Okay. Fine. So now we have K1 into 1 plus K2 to be equal to A plus B. Okay. So therefore what we have, K1 into 1 plus AB to be equal to A plus B, and K1 is equal to A plus B upon 1 plus AB. Now by just simply visualizing these things, so what we wanted to figure out was magnitude of K1, which is equal to magnitude of A plus B divided by magnitude of 1 plus AB. This we need to figure out. Okay, so what it will have basically, what is the magnitude it will have basically. Now it's difficult to figure out in this fashion, so what we will do, I just try to plot it. So what have I plotted? I have plotted this F is basically my K1. So I have plotted K1 as a function of A and B, and if you observe, the minimum value that it can take is -1 and the maximum value it can take is +1. So by this figure, we can find that the minimum value of K1 is -1 and max value of K1 is 1. So this means that my K1 belongs to -1 to 1, which means that my magnitude of K1 is less than or equal to 1. Is it clear? Let us try to do it in a in different ways, let's say. Okay, so let me just take this. So we have this K1 as a plus b upon 1 plus ab. So let me do this. We have a plus b magnitude square is a square plus b square plus 2 times ab. Now this magnitude, like this, we have magnitude of a is less than or equal to 1. So this is less than or equal to 2 times 1 plus ab. Let's not do it right now. I'll post the mathematical view of this online in the portal. Let's not mess up what we have done right now. Okay, are there any questions in this part? Any questions on whatever we have discussed? Okay. Okay, so let's, if there are no questions in this part, then let me move on to the next last question that I have planned to cover today. Okay, so here what is given to us is x1 by x1, sorry, y1 of z upon x of z is equal to, so this y1 of z upon x of z is equal to 1 plus 2.5 z inverse plus 0.5 z to the power minus 2. And what we need to find? We need to find the value of k1 and k2. So if we compare, this is, so what we had got in the previous question is something like this. So this y1 of z upon x1 of z is equal to this equation. So I'll just rewrite that equation on the next page. So what do we get? So we get 1 plus k1 into 1 plus k2 z inverse plus k2 z to the power minus 2. So again, by comparison, these two things are same, and similarly these two things are same. Just different color. Yeah, this and this is same. So therefore my k2 is equal to 0.5 and k1 into 1 plus k2, this thing comes out as 2.5. Okay. So therefore my k1 is equal to 2.5 divided by 1 plus k2, which is equal to 2.5 divided by 1 plus 0.5, which is equal to 2.5 divided by 1.5. And if I simplify this comes out to be equal to 5 by 3. And this k2 I can also write as 1 over 2. So therefore we get k1 as 5 by 3 and k2 as 1 by 2. Any questions? Any questions in this part? Okay, if there are no questions, then before ending this class, I will just like to mention few things. First thing I would like to mention is this kind of structure that we just saw in last two questions is known as lattice structure. And on this structure, we'll have a lot of content in the 11th week. So in the 11th week's tutorial, we'll be majorly focusing on the lattice structure and the questions related to that. So this is an important and a nice way to represent any filter, any rational filter. We'll see how to represent an IIR and an FIR filter using this particular lattice representation. So to summarize this week's session, since we are left with few minutes, what we can do is, so this week basically ended the filter designing part of this course, which is the most fundamental part of this course and most important part of this course. And we looked at various windows, and we used FIR, we used the criterias and we saw how to design the different kind of filters using different types of windows as well in this class. And then we discussed few things related to signal flow graphs and other stuff. So how to get the signal flow graph of the system from a given transfer function. That was the first thing that we did. And then we saw how to do the the opposite thing. That is how to get the transfer function from the given signal flow graph. Okay. And at the end, we just introduced a little bit of lattice structure, which we will be looking at in a greater detail in the coming week. We'll also look at the different types of system representations. For example, if we have small blocks of systems, which we already have, and the resultant system, the bigger system, what we have is either product of those blocks or addition of those blocks. So how to use the small already available blocks to represent a bigger system. So there are two ways to do that. One is using parallel form and another is the cascade form. So these two things also we will be seeing in the coming week, in the week 11, along with the lattice structure. Is it clear? Any questions till this point? Any questions on anything that is related to whatever I have covered today in the class? Okay, if there are no questions, then thank you for attending today's session, and I'll upload the video and this lecture soon on YouTube. Thank you. Hope to see you all in the next week as well.